Congratulations, you've decided to have a Friday night at a physics lecture. A bunch of very curious people over here. Thank you for the applauding. Very good. Applauding yourself. I respect that a lot. Do we have any physicists here today? Do we have any non-physicists here today? Wow! There's a lot of people learning from scratch. That's a new good sign. We have a little competition to go on. You can get yourself a Science and Biz hat, so you can be cooler than everyone else. The next Friday night you don't have a science lecture. Does anyone know what Einstein's famous formula, can we call it that, is? Yeah? Yeah, that was quick. What is it? E equals mc squared. Is that's correct, right? Yeah, okay! You can tell I'm a social science major and not a STEM person. So the way Science and Biz works, has anyone been here before? A bit louder? Yeah. Anyone not been here before? Okay, the newbies are outshining you. You've got to get your stuff together. So what happens is, first we have a 45-minute lecture where you will learn lots of exciting things about the universe and gravity. Is that on the right track? Yeah? Again, social scientist, not a physicist. And then we will have a beer break. Anyone know what happens at the beer break? Get a beer, exactly. And then after the beer break, we will finish with the lecture, and then at the end, we will take questions. Does that sound good?
Yes.
Okay, perfect. I think it's up to you, Sofie, to start off. Can we give her a round of applause, please?
Thank you. Just as beginning information where I can check that everyone can actually hear me, I think you said 45 minutes. I think I was told 20, 25 minutes, then a break. Then 20, 25, 30 minutes. Yeah. Okay. I'm really happy that you showed up. Earlier today, I realized it's Black Friday. No one's going to show up. And then I realized, oh no, it's also the biggest Christmas lunch weekend. So I'm just going to show up here and be told you can go home again because no one's going to be here. So I'm very happy you're here. Thank you for that. So I'm a researcher at the University of Southern Denmark here in Odense, where I work at CP3 Origins, which is a center for cosmology and particle physics phenomenology. And my research subject is cosmology, which means I study the universe as a whole. So the questions I think about when I'm at work are, has the universe always existed? Or did it at some point just appear out of nowhere? And if so, how? How's the universe behaving right now? What is the content of the universe? Will it always exist or will it vanish one day? And the onset for answering these questions is general relativity, which is a theory that Albert Einstein presented in 1915. And today, more than 100 years later, it's still considered the best theory we have for gravity. So in this theory, Einstein said that gravity is an illusion. So what we perceive as gravity is really a question of space-time curvature. So to understand space-time curvature, we first need to know what space-time is. And well, space-time is just space plus time. So already 10 years earlier, Einstein realized that space and time get mixed up when we move relative to each other. So that means that if I put on a watch and take out a ruler and I run really fast across the floor, then you would all be seeing that my watch is running a little bit slow and my ruler is a little bit too short. I, on the other hand, would be seeing exactly the same for you. I would be saying your watch is too slow and your rulers are too short. So when we move relative to each other, what we perceive as time and what we perceive as space gets mixed up. So for that reason, instead of talking about space and time as separate entities, we just considered one single entity. So I kind of think of it like a cheese, like a block of cheese. It's only three-dimensional. Space-time is four-dimensional, but let's think of a block of cheese, and then we slice it. And one part of it becomes time, and the other one becomes space. But then when we move relative to each other, that just means we're slicing the cheese differently. So what we call space and what we call time gets mixed up. Okay, so that's why we talk about space-time. It's four-dimensional, so we can't really imagine it or picture it, but it is just, instead of saying only where you are, we also want to know when are you there. But then in general relativity, the space-time also has to curve. So that's, again, something that's very difficult to picture for a human brain, but we can get a nice intuitive idea of what does space-time curvature mean by imagining that we're holding like a stretchy fabric stretched out between us. So that the surface of the fabric is two-dimensional. So there are only two directions, this way and that way. And if we throw a baseball onto that fabric, then it's going to make a dent in the fabric where it ends. And that dent is how you should think of space-time curvature. It's like a dent in a piece of fabric, but in 4 dimensions. And then if we throw a marble onto this piece of fabric, it will also make a dent in the fabric, but the dent will be smaller because the heavier you are, the bigger a dent you're going to make in the fabric, and also the bigger dent you're going to make in space-time. So when in this figure, when you see the sun, it makes a big dent in the space-time, and the Earth only makes a very small dent because the sun weighs about 300,000 times as much as the Earth. So it makes a much bigger dent. Okay, so that's how you should think of space-time. When you hear space-time, just think it's a dent in a stretched out piece of fabric. But as a physicist, I need to be able to compute with space-time. I need to know how to work with it mathematically, and for that I use Einstein's equation. So Einstein's equation is not E equals mc squared. He also, found that equation, but this one is also a quite important equation. It is like the mathematical foundation for general relativity. And on the right-hand side of the equation, what you insert there is really just the distribution of matter in the system you want to describe. So let's say we wanted to describe the solar system, then we write up on the right-hand side, we write there's a sun, it's so-and-so big, weighs so-and-so much, and there are the planets, and they're placed like this compared to the sun, and they're this size, and they weigh this much, and then there are the asteroids, and so on. So we really just write up, where is everything placed, how big is it, what does it weigh? And then the other side of the equation, that describes how space-time curves. And in words, this equation then says that it's the space-time curvature that tells matter how to move, but it's a distribution of matter that tells space-time how to curve. So to understand that, we can just again look at the fabric. We have like this stretchy fabric we're holding out between us. It is where we place our baseballs. That's where we get the dents in the fabric. So it's a distribution of baseballs that determine how the fabric is going to curve. But on the other hand, these dents in the fabric are also going to affect how other objects move. So if we throw a marble onto the stretched out piece of fabric, then it will eventually begin to follow like the curvature of the fabric, and then it will roll down towards the bottom of one of the dents that it's closest to. And if we roll a marble across the fabric, it's not just going to take like a straight line over the fabric. It's going to follow the curvature of the fabric and move like this. So the curvature of the fabric, or the curvature of space-time, determines how the objects are going to be moving. Okay, so that's what this equation formalizes. And if we want to actually use the equation, what we typically do is we insert a distribution of mass on the right-hand side, and then we guess what the left-hand side should be. So of course we do very systematic methods for guessing. We use mathematical methods, but in principle we're guessing. We don't know what it's going to be, and that is what we want to know with this equation. We want to know what is the space-time curvature going to be. So when we've guessed what the space-time curvature is, we say we have solved Einstein's equation. Because then we know how the space-time is curving, and then we know how objects are going to be moving. And the first thing that was studied with this equation was the solar system. And Einstein himself, right after he found this equation and decided that describes space-time curvature, then he said, like, okay, what does my equation say about the solar system? And he had a big task in front of him for figuring that out, because on the right-hand side he had to place a sun, and then we have a bunch of planets, and we have a bunch of asteroids. So it's a lot of things you have to write up in your right-hand side of the equation, and it's actually really, really complicated to then start guessing, okay, what's the corresponding left-hand side, especially when you don't even have a computer in 1915. So what he did was, he was like, okay, I'll just find how does the space-time approximately curve in the solar system. So he just inserted the sun on his right-hand side because he knew that, okay, the sun contains about 99.89% of all the mass in the solar system that is in the sun. So if I just insert the sun on the right-hand side of the equation, then that is still going to approximately describe my mass distribution in the solar system. And then, so that's just a sun, and then you can fairly easily assess what is the right-hand side, at least what is it approximately. So that's what Einstein did. And then when he knew approximately what is the space-time curvature around the sun, then he could reinsert the planets and see how they moved. And supposedly he has himself said that he then got like heart palpitations when he saw what his theory revealed about the orbits of the planets. Because in 1915, there was a little bit of a problem with the orbits of the planets. They did back in 1915, they had a very good understanding of the planets and their motion, because already in the beginning of the 1600s, I think in 1606, I think Johannes Kepler realized by looking at measurements of how especially Mars moves over the sky, he realized that the planets' orbits are ellipses, so like circles that are a little bit squashed. And then he had studied them for a while and knew like a lot about how fast the planets move around the sun. And if we fast forward to 1687, Newton presents his theory of gravity, which predicts or can describe how these planets move around the sun. So when we fast forward to 1915, we know a lot about the planets. But we have this problem that from the middle of the 1800s, Mercury, people had realized that Mercury is actually not behaving exactly as it should. At that point, they had gotten really good telescopes. So telescopes were completely new when we were back in like Johannes Kepler's time, when he was like looking at Mars. That was something that was done just with the eyes, or the naked eyes. But in 1850s, or the middle of the 1800s, they had really good telescopes. And when you have really good telescopes, you can track the planets across the sky very precisely. And what people realized was that Mercury's orbit is a little bit off compared to what Newton's theory of gravity is predicting. The solution was very simple. If it's a little bit off, then probably it's because there is a planet we haven't found yet, which is really close to Mercury, and through its gravitational attraction can be pulling a little bit on Mercury's orbit. So, okay, if that's true, then we can take the observations of Mercury's orbit, plug it into Newton's law of gravity, and then we can calculate where should that planet be, and then point the telescope there, and then we'll find the planet. The problem was that they pointed the telescopes there, and the planet wasn't there. It wasn't a planet, or it wasn't a problem immediately, because okay, it was supposed to be very close to the sun, and it is very hard to observe things very close to the sun. And it was a really good idea to invent a planet. They had done it earlier, these astronomers. They had realized that Uranus, which is a terrible word in English, it's so much better in Danish, but that planet, its orbit had also been a little bit off compared to what Newton's theory was predicting. But then they had like put their measurements into Newton's equations and calculated where could there be this secret planet, or a planet we haven't seen yet, that can be pulling a little bit at Uranus. And then, it's a terrible word, but then they found Neptune. So they had done that before, okay? They had seen a mismatch between observations and theory and used that to predict a new planet that they then found. So they were just doing the same thing. This time they also named the planet Vulcan, which is where Spock from Star Trek is from. But this time they weren't quite as lucky, because Vulcan does not exist except in Star Trek. That planet does not exist. People looked for it, and as the decades went on and nobody found it, it became more and more problematic. But the solution didn't come until 1915, 1916, when Einstein saw that, okay, well, with his theory, the predictions for Mercury's orbit is exactly as we observe it, without any invisible planets. So that meant that astronomers especially, but also physicists in general, were like really happy about general relativity very quickly. And Einstein, he was actually not the only person to be looking at the solar system with his equations at this time. An astrophysicist from Germany, Karl Schwarzschild, was also looking at Einstein's equation, and he was also looking at, okay, what does this equation say for the solar system? And just as Einstein had only put the sun on the right-hand side of his equation as the distribution of mass in the solar system, so did Schwarzschild. And then unlike Schwarzschild, or unlike Einstein, Schwarzschild found the exact curvature on the left-hand side of the equation. Einstein had been a little bit lazy, only found like what is approximately the corresponding curvature, but Schwarzschild found the exact curvature, and therefore we call that solution for Schwarzschild's solution today. And it is probably the most well-known, or no, it's definitely the most well-known solution to Einstein's equation. And that's not because it describes the solar system, but it's because Schwarzschild, when he found his solution, he sat down with a piece of paper and played a little bit with that solution. So he looked at, okay, what's going to happen if I take the sun and make it heavier without making it bigger? So just making it more and more dense, more and more compact. And we can easily get an intuitive idea of what's going to happen by thinking of that stretched out piece of fabric, because if we throw a baseball onto it, that is made of plastic, it'll make a small dent. If we throw a baseball onto it made of wood, it will make a bigger dent. And a bigger dent, again, if it's made of lead, and so on, heavier and heavier, it's going to make a bigger dent. And at some point, the fabric is going to break. And at that point, the analogy between the space-time and the fabric also kind of breaks, because space-time doesn't break if we make the sun too heavy. Instead, Schwarzschild, he found that when he made the star heavier and heavier without making it bigger, then the curvature eventually became so extreme that the space-time just closed in on itself. So we cannot really picture that, but what it means is that if you get too close to the sun, this very, very dense sun, then you can never get away again. All directions will be pointing inwards. So that means that nothing, not even light, can get away from these areas. And therefore, we call the areas for black holes. So black holes are not actually holes in space-time. They're just regions of really extreme curvature where nothing can get away because space is curving so much that everything is pointing towards the center of the sun. And Einstein did not believe that black holes existed. It's not just a rumor. I checked it. Found a paper from 1939, I think, where he writes that they are ridiculous. There's no way they exist. Today, we definitely believe they exist. We believe that black holes are distributed throughout our galaxies, or all the galaxies. These small black holes, they're called, they come about by having a star like collapse in on itself. Then it becomes a black hole. And we think that all galaxies have a huge black hole at their center. We don't know quite how they come about, but we do think they're there. We even have pictures of them. The first picture we got in 2019, that was a picture of the black hole called M87 star, which is the center of the galaxy called M87. And then 2 years later, we got this picture, which is a picture of Sagittarius A star, which is the center of the Milky Way. So this is the center of our galaxy. And in 2021, when this picture was released, there was like big press conferences, and it was a very big day. And I happened to sit in the office next to one of the guys working in this collaboration, in the Event Horizon Telescope collaboration, which is the collaboration that took these pictures. And they had these satellites here. So they have satellites like this spread out all over Earth, and then they combine their information to make a picture of this black hole. But the colleague here, he was very kind to show me that there's this link where you can see how these telescopes, how they like zoom into the center of our galaxy. So it's a 30-second movie that I'll just show you because it's kind of nice, I think. So all you have to concentrate about is just, seeing how neat it is that we, with these telescopes, can zoom in on the center of our galaxy. So there's a lot of zooming to get that picture. And I've heard that some physicists cried when they saw this because like there's so much hard work in getting that picture. So I'll forgive them for the resolution is not top notch, but they also really had to zoom. So okay, this is very nice. One can maybe wonder what are we actually looking at here because you can't see a black hole. No light can escape from it, so it should be invisible, or at least black. And what we're seeing here is of course that. So there's a ring of light, and in the center of that, there's a dark area. And the dark area is roughly the black hole. And what we're seeing is that there's a lot of light from stuff outside the black hole. And then where the black hole is, it'll make like a shadow on that backdrop of light. So that's what we're seeing. And this is very, very neat. It's really neat that we can describe black holes, predict them and see them, and that we can describe solar systems. It's very cute that we can do this with general relativity, but I'm a cosmologist, so I don't want to describe just one black hole or one solar system. I want to describe all of them, and I want to do it at once. So on the right-hand side of Einstein's equations, I have a lot of stuff I need to write up because our own galaxy contains a few 100 billion stars and corresponding solar systems, and there are a few 100 billion galaxies in the visible part of the universe, so the part of the universe we can in principle see with our telescopes. So it's really a lot of stuff one has to write up on the right-hand side of Einstein's equation if one wants to describe the universe. It's of course completely not feasible to do. But even if we could do it, just let's pretend we could in principle do it, then we have to guess what the left-hand side is. So we cannot do that in any way. So if we want to describe the universe using Einstein's equation, we have to introduce some kind of approximation, the same way Einstein and Schwarzschild did when they just wanted to describe the solar system, only introducing the star or the sun. We have to do something similar here. And Einstein, he set himself the task of figuring out what can I write on the right-hand side here in 1917, when he, as the first person, wanted to use this equation to describe the entire universe. And the approximation he introduced is called the cosmological principle, which is just a very fancy way of saying that we're describing the universe as a glass of water. So if we look at a glass of water with like the naked eye, we see a completely homogeneous distribution of fluid. There's the same amount of water everywhere in the water. It's a completely homogeneous distribution. But if we zoom in on the water very, very much, then we'll see that it's actually made up of water molecules. And these water molecules, they contain all the mass in the water. Between the molecules, there's absolutely nothing. And then if we zoom in on a water molecule, an H2O molecule, we'll see that it's made up of 2 hydrogen and 1 oxygen atom. And again, all the mass in the molecule is in the atom, in these 3 atoms. Between them, there's absolutely nothing. And if we zoom in on the atoms, we'll see that one atom will consist of 1 or more electrons that are orbiting a nucleus. And the nucleus is teeny tiny compared to the entire atom, but it contains over 99% of the entire mass. And the nucleus can also be split up to smaller components, first neutrons and protons, which can then again be split up to quarks and gluons. So when we look at the water zooming in more and more, we'll see that it actually represents a very inhomogeneous distribution of matter. But when we zoom out, we are erasing the structure, and these inhomogeneities, they vanish. And when we look at the water with our naked eye, we're viewing it at very big scales compared to the scales where the structures are. So we just don't see them. We see a completely homogeneous distribution. And the same thing happens in the universe. On small scales, there are stars, and these stars, they clump together in galaxies, and galaxies, they clump together in clusters of galaxies, and if those clusters are big enough, we'll call them superclusters, but there is like a limit to how big they get. So if we just zoom out above this limit, then the distribution of matter in the universe is exactly the same everywhere. So the content of the universe becomes completely homogeneous. And writing up or inserting that in the right-hand side of Einstein's equation is fairly easy. And then it's all for a physicist and mathematician, at least. And then it's also fairly easy for Einstein, let's say, to figure out what the corresponding left-hand side is. So that's what he did. And he was very unhappy with what he found. And I don't know, is it okay to have a beer break now? And let that be the cliffhanger? Yes, so we'll do that.
Can we get a round of applause?
Can we get a round of applause?
Today's beer is called, what's it called again? Schlagerfest, thank you. My German is not great. As you can see, I enjoyed it very much. During the break, have a think about how it relates to today's lecture, and you can win a hat afterwards. Okay, enjoy. Everybody got a beer in hand. Just quickly before cheers to you too. Just before we start, I've got an ID from someone called Thomas from Munkensdam Gymnasium. Yeah. Now the identity theft has been solved. We can continue. Did anyone work out the link between the beer and the talk today? Oh, I think you were first.
Well, Schlager music is German, just like Einstein.
Oh, so good. A round of applause. Fantastic. I think we will start. We'll take questions at the end, but I think we'll continue with the second part of the lecture. If everybody's ready for some more science, for your minds to be blown again about how big the universe is.
Did you Google that Einstein is German?
No.
I don't think he's German, but okay. He worked at Berlin University.
I did Google.
Oh, is it?
This, so I didn't look like an idiot. And Google says he was at least born in Germany.
Yeah.
So
Oh, okay. Yeah,
some
okay.
philosophical issues about identity, but
He moved around a bit. Okay. I guess he ended up being American, but yeah. And he worked at Berlin University when he found or made up general relativity. I'm just saying random stuff so that it quiets down. Okay, so Einstein described the universe as a glass of water. He put that into the right-hand side of his equation. Then he got the left-hand side, which is supposed to describe how space curves, or space-time curves. And then he was very unhappy with what he found, because what he found was that the left-hand side of his equation say that not only can space-time curve, it's also dynamic. So he found that a universe will be expanding slower and slower and slower, and then it will eventually stop up and begin to collapse. So the universe behaves very much like a ball that's being thrown into the air. It also moves slowly, slower and slower. Then it reaches like a top point where it stops for just a brief split second, and then it starts falling down faster and faster. And it does that because of gravity. So that the fact that the universe behaves in a very similar way when described using this general relativity, or Einstein's equation, is maybe not so surprising, but Einstein was really not happy with it, because at this point in time, in 1917, there were no observational evidences that indicated that the universe was anything except static. So it's fine that there were some orbits of the planet, so on, but it didn't look like the universe itself was doing anything. In fact. Yeah. Okay. So in fact, this equation that I've shown here it's actually the same as the equation that he had on the cup, or that was in the cup before, but I completely dropped what I was saying. There was a ball. And it falls down, and the universe is behaving in exactly the same way. According to his equations, either it is expanding or it's contracting. And that is not what people expected at this point, also not Einstein. So everyone thought that the universe is behaving today as it is today, as it always has been, and it always will be, and it's definitely not expanding or contracting. So Einstein didn't believe his results. So this is the equation that I've been showing on the cup a few times. But I've highlighted one of the terms here. It's red, and that's because that term was actually not there when he introduced his equations in 1915. But he introduced it now because he realized that, okay, so I don't believe that my equations can be correct because they show the universe is expanding or contracting. But if I introduce this term, he found, then he could actually stop that dynamics. So the V here, that's like upside down V, is actually a Greek letter lambda, and it just symbolizes a constant number. It's called a cosmological constant because it's a constant, and then we use it in cosmology. But he realized that he could like fine-tune the value of that number so that he could just exactly get the dynamics of the universe to stop. So he could stop the universe, place it in the position right between where it expands and begins to collapse. So what corresponds to the top of the ball's curve. So he did that. And then later he then called that his biggest mistake ever, because the observations then began to show that the universe actually is expanding. So so this was in 1917, right? And then a very few years later, in 1922, Edwin Hubble, an astronomer in California, was sitting on a mountain and having access to the biggest telescopes at that time. And he looked out and he saw not just stars, but he also saw these fuzzy areas that people had seen before. It's just like there were these fuzzy blobs on the sky and no one really knew what they were. But in his telescope, he could see that these fuzzy blobs were actually also blobs of stars. So they contained individual stars that were way, way, way further away than the stars you can see just like with your naked eye. So he realized that the universe doesn't just contain the Milky Way as one galaxy, but it contains loads of galaxies. And then a few years later, he was on another mountain in California looking through an even bigger telescope that had just been built. And then he saw that all these galaxies, they're moving away from us. So what he saw was that he was like in galaxy A, and he saw all the other galaxies, they were moving away from him. And then, okay, if you see that, then the immediate conclusion could be that, okay, then we're like at the center of the universe and everything is like moving away from us. And no one likes that idea. So the other option is, the only conclusion that physicists, including Edwin Hubble, were happy with was to say that, okay, if we see this, we sit here in our galaxy, see everything moving away from us, then that is what I would also have seen if I had been sitting in any other galaxy. So if I were sitting in galaxy B, I would just be seeing exactly the same thing. All the other galaxies moving away from me. So if all galaxies are actually moving away from all other galaxies, then that means that the galaxies aren't actually moving. Instead, it's just the space between the galaxies is expanding. So it's exactly as if we use a marker to put dots on a balloon, and then we inflate the balloon, and then the distance between the dots also increases, not because there are little motors on the dots that are making them move around, but because the fabric of the balloon is being stretched out. Okay, so that's how we interpret Hubble's observations. We're sitting here in galaxy A, so we don't actually know what they see in galaxy B. But our interpretation is that since no one so far has come up with a very good reason as to why we should be at the center of the universe, then our assumption is that we're not, and that space is actually expanding, and Einstein was right. His original version of general relativity was correct. So Einstein, he didn't really believe Hubble's observations to begin with, but after like 5-ish years or so, he went to Edwin Hubble to California, looked at the data and said, okay, introducing the cosmological constant was the biggest mistake I've ever made. Let's throw it into the trash. And then for 100 years now, we have been making even more observations, very many different types of observations in the universe. And we have then used these observations together with general relativity, together with Einstein's equation, and we have gotten a very good picture of how the universe appeared, or how the universe's history has been. And it's summarized in this figure where we're over here. So even though there are 2 arrows here, time is going that way. So this is today. And the universe then appears to be about 14 billion years old. So if you have a universe that's expanding today, then when you go backwards in time, the universe gets smaller and smaller and smaller. And eventually, if you just keep extrapolating, you reach a point where the universe just has no extension anymore. It doesn't extend anywhere, so the universe disappears. And that seems to have happened about 14 billion years ago. We're not quite sure if that is actually what happened, because when we go backwards in time, then when we reach a teeny tiny fraction of a second before this like 0.0, general relativity breaks down. And that's because quantum mechanics begins to be important in the entire universe. And quantum mechanics is like, it's a set of rules that everything in the universe has to obey. So it's a set of rules that all physics also has to obey if it wants to describe our world. And quantum mechanics it's only important on small scales when you want to describe like individual particles. And on those small scales, general relativity normally doesn't matter Gravity doesn't matter on those small scales because particles have very small masses. So it's like teeny, teeny, tiny, negligible dents in space-time that they make, like individual particles. So on small scales, that's where quantum mechanics is important, but general relativity isn't. Then if we go to the big scales, macroscopic scales, scales where we look at the world that we can see with our naked eyes, then quantum mechanics is no longer important, but general relativity is. Gravity becomes important. So normally, it doesn't really matter that general relativity and quantum mechanics can't be combined, but they can't. And that becomes a problem in this like teeny tiny first fraction of a second of what appears to be the universe's like first time. There we need both quantum mechanics and we also need general relativity to describe what's going on, because when we like go backwards in time and the universe becomes smaller and smaller, the content of the universe is the same. So it becomes more and more dense, the universe, and when we reach this little teeny tiny fraction of a second before time zero, then the content of the universe has been compressed so much that even on teeny tiny scales where we have individual particles, even on those teeny tiny scales where quantum mechanics is important, there is quite extreme curvature space-time, the most extreme curvature we get at all in the universe. So we cannot neglect general relativity even on small scales. So to understand what's going on, we need both quantum mechanics and general relativity, and they just don't work together. The theory that can describe both gravity and quantum mechanics at the same time is called quantum gravity. And it's a name we have for a theory that doesn't exist. So it's a theory that we would like to construct it. And people have been working on that, well, in principle since 1916, because Einstein himself noted immediately after he presented his theory that actually it can't be right because it can't be combined with quantum mechanics, and it has to be. So we cannot describe this teeny tiny fraction of a second, and therefore we also don't know if it actually marks the beginning of the universe or if the universe was also there before, and if it wasn't there before, but if it actually is the beginning of the universe, then we don't know why or how that happened. So we need quantum gravity to answer those questions. But other than that, then these 14 billion years, we can describe them using just general relativity. So we know that the early universe, after this teeny tiny fraction of a second, was very, very different from the universe we see today. So today we have stars and galaxies. We didn't have that in the very early universe. Instead, we just had this like soup of atoms everywhere. It's a completely homogeneous or almost completely homogeneous soup of atoms, and mainly hydrogen, a little bit of helium atoms. And the soup was almost homogeneous, but some places they were just randomly slightly more dense than others. Slightly more particles were bunched together. And if there's slightly more particles bunched together, then they make a small dent in space-time. And the particles around it will start to fall down into that dent. So gravity is attractive, right? So it's gonna, so these overdensities will attract the surrounding atom soup. And then that way, over hundreds of millions of years, the soup of atoms is clumping together into these balls. And these balls of atoms become hotter and hotter because they become more and more dense. And when atoms are clumped together, the temperature rises because temperature is really just a measure for how much particle or atom movement you have. And if you have many atoms and particles bunched together, then you also have a lot of movement bunched together, then you have high temperatures. And it actually reaches millions of degrees just from gravity. And then when we reach millions of degrees, then the atoms can begin to fuse. So we have fusion, or they melt together. And when they do that, they emit light, and then you have stars. Okay, so that's how we made stars, and they then also clumped together. And those clumps of stars called galaxies, they also tend to clump together from gravity or from dents in space-time. And we can explain all this very well with general relativity, and we can observe it very well. The only problem is that if we want this model of the universe, or if we want, let's say, our model of the universe that we get from general relativity, if we want it to fit the actual observations we're making, then we have to have a very special distribution of matter in the universe. So I said earlier that we have a completely homogeneous distribution of matter, but that doesn't mean that there's not more than one option. There's still many options, because if we have a glass and we pour water into it, then we can pour more or less water into it. And we could also begin maybe pouring other things into it. We could pour coffee into it, or soda into it, juice into it, and mix it around. Then we still have something that's homogeneous, but now we have different fluids in our glass. And we can have more or less of that. And we can do the same thing in Einstein's equation. Even though on the right-hand side we put a homogeneous distribution of matter, then it can be a homogeneous distribution with more or less of the matter. And it can be different types of matter or energy, because E equals mc squared. So we don't really care if it's matter or energy. That's the same thing. So we can still vary what we have in the universe. And when we use different combinations and amounts of different types of matter or energy, then we get different models for the universe. And one specific combination of distribution, amount of, and different types of matter or energy, only one specific combination gives us the universe we actually observe. And that combination looks like this, where the yellow part of the pie chart, that's about 5% of the content of the universe, and that is what we call normal or ordinary matter. And normal matter, that is, well, that's everything we know it is. That's what I'm made of, you're made of, the Earth is made of, the stars are made of, the helium and hydrogen gas that we have in galaxies. All that is normal matter. The weird particles they make at CERN and the Large Hadron Collider, that's also normal particles. Everything we know it is, that is normal particles. So normal particles only make up 5% of the content of the universe. That means that we don't know what 95% of the content of the universe is. We know a little bit. We know enough to split it into two types of materials, two types of matter. We call one dark matter and the other dark energy. And we use these two components to, shall we say, solve different problems that we have observationally. So dark matter is used for a variety of different things. We have observations regarding individual things in the universe, like galaxies, for instance, that are behaving in ways that they shouldn't be behaving. But we can solve that by introducing this dark matter. So if I do like this, look a little bit silly, then my arms, when I'm twisting, will just, they'll fly out to the sides. Okay, and that's because when something rotates, it wants to be pulled apart. So my arms, they stay attached to my body because of electrostatic forces. A galaxy is also rotating and it also wants to be pulled apart, but it's gravity, or dense in space-time, that holds the galaxy together. So we can look at how fast are these galaxies rotating, and we can also look at how much mass is there in the galaxy. And there we can see how many stars are there and how much helium and hydrogen gas is there. That's all the ordinary matter there is. We can see how much there is of that, and then we can compute, okay, how big a dent in space-time will that make? And thus, how fast are these galaxies allowed to rotate without being pulled apart? And it turns out that the galaxies are rotating way too fast. They should have been pulled apart a long time ago. And the simplest solution is to say that, okay, well, maybe there's just more matter than what we counted. Maybe there's some stuff that doesn't emit that much light, then we can't see it. Now we have other observations that put constraints on how much normal matter we can have in the universe. So we actually know that if there is any extra matter, then it cannot be normal matter. Then it has to be something else, a type of particles that we don't know. So particles that we have never ever detected in any laboratory ever, and we simply don't know what it would be. But it is the simplest explanation of these galaxy rotation curves, to just say there's some extra matter that we can't see. But of course, that story sounds a little bit familiar if we think about Vulcan. So there we also had, okay, there was an orbit that was a little bit off, so let's invent a planet that's invisible. And with Uranus and Neptune, it worked well. Didn't go so well with Mercury. Right? Vulcan doesn't exist. There, the problem was that we were using the wrong theory of gravity. So now you could also think, okay, well, rotation curves are a bit off. Maybe the laws of gravity are not described that well by general relativity. And that is a possibility. It is a possibility that dark matter doesn't actually exist, but that it just kind of looks like it to us because we're using the wrong theory of gravity. And that if we modified our theory of gravity a little bit, then we would see that, oh, the rotation curves are exactly as they should be. It is a possibility, and it is important that there's research in that area, but many physicists, most physicists do expect that there actually are dark matter particles. And that's because these dark matter particles, they're needed to explain very many different things. So not only these galaxy rotation curves, and it becomes very difficult to explain all the different things with just by modifying gravity in one way. But it's very easy to explain by just introducing some extra mass. So the most difficult observation to explain using a modified theory of gravity is the bullet cluster. So the bullet cluster is where you have two clusters of galaxies that collide. So clusters of galaxies can be maybe a little bit hard to picture, so we can also just picture galaxies. It's the same principle. When two galaxies collide, the stars don't notice it at all. Because even though there are several hundred billions of stars in a galaxy, they're separated by really, really vast distances. So when two galaxies collide, almost none of the stars will come even remotely close to any other stars. So they'll just glide completely through each other. The stars from the two galaxies won't notice the collision at all. So they're lying out here in the blue regions. But most of the ordinary mass in a galaxy is actually helium and hydrogen gas. And hydrogen and helium gas is extended over like long regions. So when two galaxies collide, the gas will lie in the collision area, can't really pass each other, will lie there and interact. So it would be in this red area. And if we only have like normal matter in our galaxies, then the most of the mass by far will be in this gas, will not be in the stars. So if there's only ordinary matter, then we would see the biggest dent of space-time here in the red region, and only small dents of space-time out in the blue regions where we have the stars. And now we can actually see that that's not quite the case. And of course, we can't actually see space-time curvature as humans, but we can see pictures of galaxies that lie behind this collision, or these two clusters of galaxies. And so the galaxies behind them, they send light. We get their images that we can see in our telescopes, and we can see how those images are deformed when they move through the space-time curvature that this bullet cluster makes. And from that, we can deduce that the big dents in space-time are out here. And in here, there's only actually a quite small dent in space-time. So exactly the opposite of how it should be. And that is really, really hard to describe using modified gravity. It's really, really hard to make a modified theory of gravity that can explain this, and then at the same time also explain, for instance, why galaxies are not being ripped apart because they're rotating so fast. But it is really, really easy to explain just by introducing dark matter, because if dark matter exists, it will barely interact at all with anything, which means that it will be type of like ghost-like particles that just move through everything and each other as if they didn't exist. Because otherwise, we would have measured and we would have detected them in our laboratories a long time ago. Because if dark matter particles exist, then they're everywhere around us. There are loads of them. And we do know that this type of ghost particles exist in the form of something called neutrinos. So we do know some types of these almost invisible or entirely invisible, but also like ghost-like particles that just move through us. So we're all of us are bombarded by hundreds of millions of neutrinos every second, and we don't feel it because they simply don't interact with us. So maybe dark matter, if it exists, it will also not interact with us, and it will also not really interact with each other, these particles. So if they are in these galaxies or these galaxy clusters, when they collide, the dark matter will also not realize that there was a collision, and it will just move into the same areas where the stars are. So that's why it says DM for dark matter here. And if these rotation curves are explained through this introduction of dark matter, then dark matter will make up typically like 85% of the mass in the galaxy. So that means that during a collision, most of the gravitational effect or the biggest dents of space-time would be in the blue regions if there's dark matter. And that is exactly what we see. We see the big dents in the blue regions and the small dent in the red region. And that is really easy to explain if we have dark matter, but it's almost impossible to explain if we don't have dark matter. So because of that, most physicists do expect that there are these new types of particles that we just haven't detected yet. And physicists, we really like particles, so we're kind of happy about this. We're completely okay with the dark matter. This is slightly old numbers, so it's about 25% of the content of the universe. So the fact that 25% of the content of the universe is a new type of particles is just exciting. So it's really okay. Yeah, but see, dark energy though, it's not okay. It makes up now 70% of the universe's content today, and we really don't like dark energy because dark energy is introduced because we make observations of the universe, and these observations, they do show that the universe is expanding, but since the turn of the century, we've noticed that actually they show that the universe is expanding faster and faster. And that is not at all how the universe is supposed to behave. The universe is supposed to be expanding slower and slower, not faster and faster. If you have a universe that expands faster and faster, then it corresponds to having a ball that you threw into the air, and then instead of it falling down again, it just kept flying upwards forever without ever falling down again. Okay, so if we have a universe that's expanding faster and faster, that means we have some kind of anti-gravitational effects in the universe. And the type of matter or energy that is giving this anti-gravitational effect, we call that dark energy. Then it has a name, we can talk about it, and it sounds like we know what it is, but we really do not. But the first step for figuring out what it is to see how can we describe it mathematically. And there Einstein was really kind, because he actually introduced a really neat method for describing it mathematically. He introduced this red term, right, the cosmological constant. That was the V that's upside down. So he introduced it to make the universe static, so to like modify the gravity, control the gravitational expansion and collapse. And if you just tune that number a little bit differently, then instead of getting a static universe, you get one that expands faster and faster. So at the turn of the century, we reintroduced this red term, which is why it appears in the cup, because this is how we write Einstein's equation today. But of course, it's not very satisfying just like reintroducing this and saying, hey, yay, it fits. We want to know, what is it? Like physically, what does this term, why is it there? What does it represent? Is there some kind of substance, some kind of fluid in the universe that has this type of anti-gravitational effect? And there actually is one possible way of describing this. So it could be the energy of nothing, of empty space, which is what we also call a vacuum energy. So if we imagine like we have a box and we pull out everything in it, like we suck everything out, there's nothing left, then we have vacuum, right? And you would expect that in vacuum there's nothing, so there's no energy. But that's not quite right, because quantum mechanics comes back. And well, it has these rules that everything in the world has to obey. And one of these rules is that things are allowed to pop into existence out of nowhere as long as they disappear again fast enough. And in fact, quantum mechanics requires that particles will pop into existence and disappear again. We call this type of particles virtual particles. And they appear in pairs. So we have, in vacuum, we have pairs of particles that appear and vanish again. Elementary particles, that's the like building blocks of everything in the universe, the particles that we know, right? That's we can't break them down into anything smaller, but we can use them to build everything else in the universe. And an electron, for instance, is one of the most well-known elementary particles. And all elementary particles, like the electron, has a type of partner particle called its antiparticle. And if a real particle and its real antiparticle, they meet each other, then they annihilate. That means that they turn into light. All their energy just becomes light. But if it's a virtual particle and a virtual antiparticle that meet each other, then they just vanish. So what we think happens in vacuum is that these particles and antiparticles appear out of nowhere in pairs and then smash together and vanish again. And that happens all the time, constantly, everywhere in vacuum. So that leaves us with a little bit of energy in vacuum. Even though there's nothing really there, we do have some energy. And that vacuum energy behaves exactly as a cosmological constant. So the cosmological constant, it's a constant number. So what it actually corresponds to is that you have a fluid in your universe that has a constant density. which is really weird to have when you have a universe that's expanding. Okay, so if we imagine another box filled with a cloud, then if we make that box twice as big, then the cloud or the fog has to spread out over twice as big a volume, so it becomes easier to see through it, right? So the fog, the density of the fog has become lower. And that's also what happens in the real universe with dark matter, if it exists, and with ordinary matter. When the universe becomes bigger, the density of matter drops. But that's not what the cosmological constant corresponds to. It corresponds to something that just has like constant energy density, so that the universe becomes bigger, there just also, there comes more of this type of energy, so it has a constant density. That's very weird, but vacuum energy behaves exactly like that, because if you have a box full of nothing, make it twice as big, you just have twice as much nothing in it. Okay, you have twice as much vacuum energy because quantum mechanics doesn't care about how much room there is, how big the box is, how big the universe is. It'll just make these virtual particle antiparticle pairs everywhere. There's a question.
Yeah, this vacuum energy, this thing that we have just described of particles appearing and disappearing and annihilating itself, have we ever actually observed it?
Yes and no, or maybe. Okay, so we haven't particles are very small. We don't look that often exactly at it and can't see them with our eyes. But if vacuum energy exists, then you can do this trick where you make vacuum in a box and then you put in two metal plates very, very close to each other. Then between the plates, there'll happen this thing that there's not room. Let's think of it like that. There's not room for making quite as many particles as there is outside. So the density of the vacuum suddenly becomes smaller between the plates than it is outside the plates. And then that means that that corresponds to having lower pressure between the plates and outside. So you would have these two plates be pressed together. That's called the Casimir effect. And that has been observed. And the reigning theory is that is vacuum energy, but there are of course always, we're physicists, so we have to be skeptic and consider, could it be something else? And the astute person might have noticed that in that vacuum we put some plates, so it's not vacuum anymore. There's something in there, and could those plates maybe be interacting due to something else, for instance, electromagnetism? So you can't say 100% for sure that we have actually measured this vacuum energy, but most physicists would say, yeah, sure, we've measured the Casimir effect. So we have measured it, maybe. Yes, indirectly, yes. And there are people making lots of experiments with it. I think it's in Sweden. They've done this thing where they can have plates move very quickly compared to each other, and then they make this thing where you rip these virtual particles and antiparticles. They can sort of be ripped too far away from each other so they can annihilate, and then they can make light appear out of nothing. But it requires quite a lot of energy to do it, so they've concluded that it's not something that we can use to create energy out of nothing, because it really requires a lot of energy to pull the plates. And also people have noticed you have metal plates, so sure, you can make light. So people are, we're not quite sure, but yeah, but maybe we have measured this directly, or yeah, measured it from the Casimir effect. But it is the only explanation we have of what could be a cosmological constant, or what could be dark energy if it is described exactly as a cosmological constant, would be this vacuum energy. But okay, so we have a theory for it, so let's start calculating what it is. One could do that. What is our theoretical prediction for vacuum energy, and then compare it to the energy density we measure for dark energy and see if they fit. And they really, really don't fit. So this is the energy density of the vacuum as we compute it. When we calculate the vacuum energy, it is a 1 followed by 120 zeros times as big as the energy density we measure for dark energy. So that is called the baddest or the poorest theoretical prediction ever, because it is very, very wrong. This cannot be true. It certainly cannot be true that there is this much vacuum energy in the universe, because if there were, then the universe would have expanded so fast, so early, that none of the things we see in the world around us would ever have come into existence. The particles in the early universe, the particle soup, would never have formed stars, and there would never have been galaxies and so on. So we've made a mistake here, and we do also believe that the mistake must be due to quantum gravity, because we don't really understand quantum gravity, and maybe that will come along and fix things for us. Then the question is, how's it gonna fix it? We don't know yet, but the physics community is split in two parts, where one part says, well, it's gonna make everything fit so that we just get that the prediction for the vacuum energy density is exactly equal to what we measure. So problem solved. And then the other part of the community is saying, yeah, no, we really don't believe that, because we've made a huge mistake here. And if quantum gravity is to actually solve that so that our prediction becomes exactly equal to what we observe, then the corrections have to be precise to like 120 zeros, which is just so unlikely that the only really likely outcome is that the vacuum energy density, when we compute it correctly, will turn out to be absolutely zero. And that means that it doesn't actually exist, this vacuum energy, and that we also don't really have an explanation for what dark energy is. So we have Einstein's equation and general relativity that we can use to describe the universe. And our description of the universe fits really, really well with what we observe. And remember, it's almost 14 billion years that we are explaining with this one theory. So it's very, very impressive, and we're very proud of it. But of course, the price is that we can only get our theory to fit observations like at all if we have 95% of the content of the universe is in forms of things we really just have no idea what is. So when you're a cosmologist like me, what you spend most of your time on is thinking about, well, what is this dark universe? What is dark matter? And what is dark energy? Thank you for your attention.
I mean, that round of applause was very well deserved. So complicated, and yet you explain it so well. Personally, I'm a bit disappointed that physics has proven I'm not the center of the universe, but I'll just have to come to terms with that. Yeah, and the fact that there is energy within a vacuum, which makes me feel like I have hope for what's between my ears. So, I actually have a question for you, because you talked about the numbers in regards to the dark energy, and you said the picture, it said it was 21%, and then you said we now think it's 25. Is it because our measurements have changed, or is it coming together?
Yeah, it's not coming together, I hope. It's just our measurements are becoming more precise, and this is like maybe 20 years old. So more precise measurements change the numbers a teeny tiny amount.
Okay, does anyone have any questions? Many. Okay, we'll start over here.
Okay, I have two questions which might be related, because I have emailed you about like this really complicated field. But my question relates to the equation on the mug, on the cup. Because when do you have like an estimation of when you will have filled in like all the holes in that equation? Like when will you be done?
No.
And then I will kind of follow up the question with, do you have an estimate of when you will have calculated or have like a result of that equation?
Yes, so what we need is, so what you're asking is when do we get quantum gravity? When do we have a theory for that, right? So when do we get it to fit together with quantum mechanics? And actually, I'm kind of optimistic. So people have been working on this really long, right? Einstein noticed 1916, something is wrong, we need quantum gravity. And then on the verge between going from 1960s to 1970s, three people independently came up with string theory. One of them was Holger Bech Nielsen, who's Danish, working in Copenhagen. And string theory was a theory that they invented because they wanted to describe what's going on inside the nucleus of an atom. So they actually wanted to describe what we today call the strong interaction, which is something completely different from gravity. But when they came up with this theory, so this theory, the string theory, that's because they take the theory for a guitar string, and then they make then they pretend that the guitar string is really, really tiny, and that means that you have to combine that theory with quantum mechanics. And when you do that, one of the things that happens is that a theory for quantum gravity seems to appear. And they were very unhappy about that because they didn't want quantum gravity. They wanted to describe what was going on in the nucleus of an atom where they knew gravity doesn't matter. So it was a little bit put to the side, but other people were like, hey, but you got quantum gravity for free, so let's work with that. But it's not a done theory, and we are not sure if it is correct theory. So we only have like parts of it. Think of it as if we've got a chessboard, and we've gotten like one or two of the pieces for the chess, and then someone said like, okay, now guess the rules for chess. Guess what parts are missing, and guess what the rules are. So that's kind of where we are with string theory. We have a board, and we have some of the pieces, and one of the pieces really looks like gravity, but we're not quite sure yet. So it kind of stalled. Partially because we just don't have the maths for it. Einstein was really lucky. When he invented general relativity, the mathematics for it was already invented. So he just had to like write to people and say, hey, can you tell me how to describe this? And then they would be like, yeah, you do like this. And now people are like, okay, we want to describe this. And the mathematicians are like, yeah, that sounds cool. Let's try to figure that out. So it's very slow. And that also means that people have then begun going other directions, also saying maybe string theory isn't correct. Maybe there are other ways of going about it. So there are different branches in this field now. And one really important thing about quantum gravity is that it is only important around, Big Bang, the beginning of the universe. So it's really hard to test if a theory is correct or not. But now we have these images, which is why we're on this slide. Now we have images of black holes. And the only other time quantum gravity is important than Big Bang is at the center of a black hole, because at the center of a black hole you have like really, really extremely compressed matter. So you have very, very high density. So even on very small scales, gravity is also important. So you need quantum gravity to actually explain what's going on at the center of black holes. And it looks like whatever is going on at the center of a black hole is also actually important for how the image of a black hole looks. And now that we have images of black holes, that means we can start testing gravity theories or quantum gravity theories. Not quite yet. This image is just a teeny tiny bit too blurry, but the next images we get, they are expected to, like, people have done the calculations and they will be so precise that we'll begin to be able to test quantum gravity theories. And now that we can begin to test them, then we have a genuine chance of like having observations that can indicate what is actually the right direction. So right now we're like blindly just fumbling about, but now we're beginning to get observations that we can actually use to guide us. So I'm quite optimistic that we could have like a genuine, well-developed, good guess of a quantum gravity theory by the end of this century. Yes. Yeah.
As a layman, I'm interested to know what are the real-life implications of all these studies, this understanding of the universe, because we see on a daily basis the impacts of biology, chemistry, medicine happening in real life. In our daily lives, we get impacted by it. But when we see all this is all fascinating. But is it all pursuit of science for a future, advanced civilization? Like we saw in Interstellar, something happening, traveling to a black hole or getting away from Earth or something like that.
Yeah, so they had a Nobel Prize laureate be part of like, how do we make this semi-realistic? It's a great movie, and it is something that people actually look at. If dark matter and dark energy exist as particles or as something else, whatever dark energy is, maybe actually vacuum energy, then these are things that we can utilize. We can't utilize them right now, and what we can utilize them for, we don't know. But it's a huge resource, right? And 95% of everything in the universe we don't know what is. But think of how we can use radiation to treat cancer, for instance. What can we use dark energy for? Is it a new way of getting energy that is much greener than what we have now, and much larger amounts of energy? And dark matter particles, what can we use them for? If we can actually get contact with this dark matter world, these particles, can we maybe use them for something? So we don't know if we can use it, but of course, we will only know if we get to figure out what it is.
Another question. Okay.
Yes.
Yeah, you said when we get the next images.
Yes.
like when do we get?
Oh,
that
they
paper?
hold very tight on that.
Yeah.
They're like.
But it's not tomorrow. Is it?
Well, I don't know. No, I don't think it's tomorrow because they were like a few weeks before they'll be like announcing there's a press conference, and then everyone is really excited, like guessing what is it gonna be. But these two images, people always kind of know what it is. So next time they have a press conference, they announce we'll have a press conference soon, then people will be very disappointed if it's not a new image. But I'm thinking some years. I haven't heard of an announcement yet, so it's not tomorrow.
Do you have any more questions? Oh, that was quite the answer.
So I'm just an engineer, not a physicist. So please be gentle with me. So I heard some exciting thoughts about what makes a black hole shrink, for example, and some ideas came up about Hawking radiation, which also relates quite good with the empty space theorem you are working on. If that's not the case, there's any empty space energy. Would that also mean that black holes are not shrinking and all the energy are stored within this massive mass?
Well, okay, so let's just, so everyone knows what we're talking about. These virtual particle antiparticles that appear out of nowhere and then smash together and disappear. So if they appear very close to like the outer skirts of a black hole, it's called the event horizon. When you come inside the event horizon, you can't get out again. Okay, so if these particle-antiparticle pairs, they appear right outside the event horizon. One of them might go into the black hole, and then the other one doesn't have anything to annihilate with, so it can't disappear, and it becomes a real particle. And that phenomenon is called Hawking radiation. And that that is used to interpret that. Okay, so this particle that became real, it somehow took the information or a particle from inside the black hole and put it out. So it will mean that the black holes are slowly shrinking and evaporating. We don't know if that's true. It hasn't been measured. If it had been measured, then Stephen Hawking would have gotten the Nobel Prize. But we haven't measured it. And I think it will be quite a while before we can measure it. If it turns out that there's no vacuum energy, then I think a lot of things will be up for grabs. But there is still big questions about what actually happens here at the event horizon of black holes. So I have no idea what will happen if Hawking radiation isn't real, and if vacuum energy isn't real. It's a very big question.
Yeah.
No idea, but it would be really, really exciting.
We have another one over here.
Yeah, no, physicists are not allowed.
Yes, so I am a physicist. I want to return to these dark matter contenders, and we've been looking for these particles for over 50 years now.
Oh yeah, I forgot to say, yeah. We have been looking for them for quite a while.
Yeah, and we haven't found them yet.
Yes.
Why not?
Well, because they are elusive, or so because if they interact, so if we can even have any type of contact with them, then it will be very, very hard. So the elementary particles I talked about earlier, so the building blocks of everything in the universe. So the non-elementary particles, they can interact in 4 ways. I think of it as the 4 senses of the elementary particles. It's the only ways they can communicate, have any type of interaction with anything around them. And those 4 senses are the 4 natural forces. So there's electromagnetism, there's gravity, and then there's something called the strong and weak nuclear forces. And these dark matter particles, they interact with through gravity, because that's how we see them. They have a gravitational effect on matter around it, on ordinary matter. It cannot, though, interact electromagnetically. If it did, then we would be able to see it. Then it would emit light and we could see it. We can't see it, so it doesn't interact through electromagnetism. It also cannot interact through the strong force, because if it did, then being hit by them would more or less be like being hit by bullets. It would be something that maybe not a bullet every time you got hit by one, but it would be something that we would definitely be able to detect around us. So it cannot possibly be that they interact strongly through any of those 2 interactions. Then there's only Well, the gravitational interaction, we can't measure that in the lab for particles. It's way, way, way too weak. We don't even know if antiparticles fall up or down, for instance, because antiparticles, so they can be, so there's an individual particle. And for those individual particles, the gravitational force is so weak that it's really, really hard to measure. And one thing they like to try to measure at CERN is whether antiparticles fall up or down, because an antiparticle can mathematically be described as its partner, ordinary particle, but moving backwards in time. So there's like the idea that maybe they fall upwards. And we don't know because it's so hard to measure. They are trying to measure it, but it's really, really hard. So we don't really expect that we'll be able to detect dark matter particles with an experiment if they only interact gravitationally. They also have to interact with the weak interaction or through the weak interaction. And we don't know if they do that yet. But as the word weak indicates, it's a very weak interaction, so it will be very hard to detect it. So that is the reason we haven't detected them yet. If they exist, then they interact really, really weakly.
We have a last question over here.
Just the last one, and it's very personal, if I may. So I'm a biologist. In my everyday life and research, I do things with biodiversity and crisis and things like this. I wonder how you perceive life in your everyday research, because you look at galaxies and I look at here and present. So is there any difference does it make any difference for you to perceive life on Earth?
So I'm only me, so I can't quite know, but no, I don't think it does. No, because I mean, so Interstellar is a really neat movie, and it would be really nice if we can do that. But the problems we have on Earth, well, we don't have a planet B right now, so and it would be really, really hard to migrate, for instance, to another planet. So if we destroy this one, then we're really screwed. Because even if we go, say we could do an interstellar thing, find another planet. If we find another planet where the environment is in a way where we could actually live there, then there are probably other things already living there. Because planets, as you would probably, hopefully agree with me, planets and the life on the planet, they evolved together. So if we find another planet that's great for us, then there's already people there, or something very similar to people, and they would probably not be happy with us coming there. So it's generally not a very good plan to try to find another planet. So I think of our planet as important as anyone else.
What a good note to wrap up on. First of all, you guys are so smart. Such smart questions. Can you give yourselves a round of applause, please? So clever. Then can we get a round of applause for our volunteers, Mark and Michael? And can we get an absolutely humongous, massive, as big as the universe round of applause for Sofie?
Thank you for showing up on Black Friday.
I think that's honestly one of the biggest applauses we've had at Science and Beers for at least a long time. Very well deserved. We will be back again on the 13th of December, where we'll be learning about how music practice can make your mind and your body better. So for those of you that were here for the first time today, I hope you had a nice little taste of what we do, and you will be back on the 13th. You can find us on Facebook and sign up. And then the last little thing, just a little bit of housekeeping. If you could please put your chairs at the back before you leave, just so that our volunteers, just where lovely Michael is waving. Right there. Just stack them on up. But thank you so much and have a lovely weekend.